in this unit so far, we've looked at how to simplify rational expressions, do operations with them, solve equations with them, but now we're finally going to see what it looks like to put a rational expression onto a graph. What happens to it then? So we're actually going to encounter a bunch of different types of asymptotes. Okay, so if you remember learning about those in the logarithm unit, okay? So before, I kind of gave you that definition that an asymptote, it's this invisible wall that the function, it can't cross it and it can't touch it, okay? So that was kind of just our rough definition to start. Now we're going to get a more concrete definition of what an asymptote is. Okay, so it's an invisible line, right, that a curve approaches. Okay, so it approaches it, it gets closer to it as it heads towards infinity. Okay, so we can see our curve or our function, it's following this asymptote off into infinity, whatever direction that ends up being. And here are the different types of asymptotes that we're going to encounter. Okay. One rule, it is going to break, however. So remember how I said for logarithms, we can't cross or touch the asymptote. And that's true for logarithms. The ones we were looking at, you're never going to cross or touch the asymptote. However, in some of these rational functions we're going to look at, this curve is sometimes going to cross the asymptote, or it will touch the asymptote. Okay, and that's okay as long as it's still following it towards infinity. Okay, positive or negative infinity. So let's take a look at the very first type of asymptote we'll encounter, which is a vertical asymptote. So an asymptote going up and down, just like this one here. Okay. So these are located at the values that make the denominator equal 0. Okay, so this phrase sounds familiar, where the denominator equals 0. Well, this is just our restrictions or exclusions that we've been learning about. Okay, so wherever those restrictions are at, that's really where an asymptote lies. Okay, so let's say I was to factor this a little bit further. So both of these are going to factor into two binomials. The top one factors into, let's see, a positive 3 and a negative 1. And then the next one, I get a 3 and a 2, where the 3 and the 2 are negative. Okay. All right, so what are the restrictions here? So I would look at my factors in the denominator, set these equal to 0, and that's where my restrictions are at, right? So my restrictions, at least for this problem, what I'm not allowed to plug in for x, I'm not allowed to plug in 2, and I'm not allowed to plug in 3. Okay? So since that's where my restrictions are at, now we're learning that my asymptotes, and let me be a little bit more specific, my vertical asymptotes, or we'll use VA for short, my vertical asymptotes are located at x equals, and this is a line here, a vertical line I'm making, it's located at x equals 2 and x equals 3. Okay, so if I was to go to a graph, so even before I graph this, I know there should be vertical asymptotes at, if I go to the x-axis, find 2, x equals 2, and x equals 3. So that's what I'm expecting even before I graph this. So now let's graph it and see what happens. So here's my function. I've graphed it, and if I put in my vertical asymptotes of x equals 2 and x equals 3. Awesome, so it definitely looks like my function is following these asymptotes off to infinity. So they look good, even though this one's a little bit farther apart. That's fine. The function is still following this asymptote to positive infinity. Okay. Vertical asymptotes, there we go. Let's consider one other case with vertical asymptotes though, right? So in this function, we would expect that there would be a vertical asymptote at x equals 2, because that's where our restriction's at. We can't plug in 2, so that's where we should find a vertical asymptote. Okay, so before I graph this, I'm expecting that at 2, there's this asymptote here. Okay, now let's actually graph it and see what happens. Okay, graphing it. Huh. Okay, so let's plug in the asymptote, like x equals 2. Huh. So it looks like it's not following this asymptote, and unfortunately they're both green right now. But it's not following this asymptote to positive or negative infinity. It's not following it. It's kind of just like, it doesn't really care about the asymptote. It's not following it at all. So let's zoom in a little bit more, maybe to that spot where they're touching, and see what's happening here. Okay, so let's look at this spot too. Whoa, okay, that's weird. So it looks like right at that spot, x equals 2, on our function, it says it's undefined. There's a hole that appears in Desmos, okay? So what's happening here? What is going on? Why is there just like this line, and then there's just like a little hole right there? Okay, so to get some answers about that, let's see what happens if we maybe factor this a little bit further. Okay, so if we factor the numerator, well, this is going to factor into x plus 1 and x minus 2. Okay, so even though there is a restriction at 2, like our restriction is at 2, we can't plug 2 in, we know that after we do that, like the very next step is to simplify and cross stuff out. So we would cross these x minus 2's out. So then we're just left with x plus 1, which is that function that we're seeing there on the graph. This is x plus 1. Like if I was to graph the line x plus 1, it lies right on top of it because these are both the exact same thing. This is what it's simplified to. So what's happening here? Well, whenever this occurs, where I cross out my restriction, or I cross out my asymptote, essentially, this is called a removable discontinuity. Okay, so I removed the spot where there was a restriction, or it was discontinuous, okay, where the function was not continuous the whole way through, okay? There was a little gap there right at 2. So in this case, there is not a vertical asymptote for this at all. I didn't see that the function was following that line off to infinity, so there wasn't a vertical asymptote. Instead, there was this removable discontinuity. Okay, so review of vertical asymptotes. Again, they're just wherever the denominator equals 0. So where we found our restrictions before, that's where we have vertical asymptotes. Except in the case where we have a removable discontinuity, where we can cross that restriction out, then it's not a vertical asymptote. Then it's a removable discontinuity. All right, and then the very last thing we'll look at for this video is 2 cases of horizontal and oblique or slant asymptotes, okay? Oblique or slant is just like a fancy way to say diagonal, okay? It's just like a diagonal asymptote. All right, so to encounter these in the function, you're now going to consider the degree of the numerator versus the degree of the denominator. So if you forgot what degree means, that's just the largest exponent in the polynomial, okay? So this polynomial would have a degree of 3 because that's the biggest exponent. All right, so now let's consider the case where the degree of the numerator, okay, well, the degree of this numerator, the highest exponent, is just 1 here, okay? So if that's the degree is 1, and the degree of this is 2, well, since 1 is less than 2, the numerator's degree is less than the denominator, okay, the horizontal asymptote is always going to be y equals 0. Okay, so if this ever happens where the degree of the numerator is less than the degree of the denominator, we're always going to get a horizontal asymptote. Okay, so I'm expecting to see, before I even graph this, if I go to the y-axis, draw a line, a horizontal line at y equals 0, this is where the asymptote should be. So let's graph this to see for sure. Okay, so we have this function here, and if I put in the asymptote y equals 0, yes, our function is following that towards positive infinity in this direction and then negative infinity in this direction, okay? And here is the case where I was talking about, where sometimes your function, it might cross or touch that asymptote, okay? So here it's crossing it and it's touching it, and that's totally fine, just as long as it's following it to positive and negative infinity. Okay, and then the very last thing we'll look at is when the degree of the numerator, so both of these have a degree of 1, when the degree of the numerator and the denominator are equal, okay? So if this ever occurs, then the horizontal asymptote is going to be a ratio, or a fraction, of the leading coefficients. Okay, so here, 3 and 4, these are my leading coefficients, and together is a fraction that makes 3/4. So I'm expecting, before I even graph this, to see a horizontal asymptote right at y, and I go to 3/4 and draw a horizontal line. Okay, so if we graph this, so there's our function, and I throw in the horizontal asymptote y equals 3/4. And definitely that is where I see the asymptote for this function. Okay, we'll look at 2 other examples of horizontal and oblique asymptotes in the very next video.